Most developers think constraints like not null, default, or check are just nice to have, optional at best. But in reality, ignoring them can silently corrupt your database. Let me show you what I mean. Imagine a column that allows null values for a status column. What does a null status even mean? Is it pending, failed, or forgotten? You don't know, and that ambiguity can ripple through your application. Or take check constraints as another example. They are your last line of defense against invalid data. Unless you skip them and let a negative salary number slip into your system. In this video, we'll break down how these three constraints really work and how to use them to make your SQL code safer, smarter, and robust. By the end, you'll know how to use the three constraints effectively to enforce business logics when it comes to translating your database design to SQL code. Let's start with the not null constraint. A null value represents a value that's missing or unknown. It can cause unexpected troubles when you are not aware. For example, when you are trying to do some aggregation calculation, but accidentally involves even a single null value, the result can be null. The not null constraint helps ensure that a column doesn't accept null values in SQL. Whether you are talking about data insertion or update, it doesn't matter. That column that comes with a not null constraint will not accept any null values. The usage of not null constraint is simple. For example, think about a table representing users in a database supporting an online store, which has quite a few numbers of columns that shouldn't accept null values, except for the phone number column. Translating this business logic to SQL code, you will have something like this. As you can see here, the code snippet lists not null constraint in the same line as soon as a column is defined. You may wonder if not null is a constraint, why we don't name them in the same manner as other constraints like the primary key constraint or foreign key constraint. People who design database systems see not null as a fundamental column property, like data type or length. Same as how you don't name the data type of a column, you don't need to name a not null constraint either. As a matter of fact, most database systems don't support naming of not null constraints at all. Beyond that, you may notice that we gave a not null constraint in the primary key column, the email column. Is that really necessary? Technically speaking, it's redundant, because if the primary key constraint is applied to a column, that column will not accept null values. However, this is still a recommended practice, because if you change the primary key constraint in the future, you don't need to worry about where to patch up in terms of the not null constraint. In other words, this small redundancy is future-proof. Last, not every column requires the not null constraints. I'm not talking about the business logic. Sometimes it can come from the requirement of an optional relationship. For example, think about the relationship between customers and automobiles in a database supporting car dealership software. The two entities are in a one-to-many relationship. A customer can correspond to many cars, and the foreign key goes to the many side, or say, in the automobile entity. Yet, both main cardinalities of this relationship are 0, which makes the relationship optional. The implication of such a design is that when a row of automobile data is added, it doesn't have to be associated with a customer at all, which will translate to the foreign key column in the automobile table, allowing null values. In summary, optional relationship, or say two main cardinalities as 0, would translate to foreign key columns that allow null values. In such a case, you need to be careful and shouldn't apply not null constraints to every column without thinking. That's everything about the not null constraint. Let's move to the default constraint now. The default constraint is used to ensure that a column always has a value. The value is either specified by the user or the constraint. Well, it's more often specified by the constraint rather than the user. Let's look at an example. Think about two related tables, purchase and a payment method, from a database supporting an online store. The purchase table represents the order records, and the payment method table represents the payment methods used by users. There is one column in the purchase table named the purchase time, which is used to record the exact time when a user puts an order online. This is a perfect scenario for you to use the default constraint, instead of relying solely on the software developers to do the right thing. You can lessen their burden by setting the default value of the purchase time to be the time when a new row of purchase data is added. The syntax of the default constraint is simple. Add the default value to the same line of your column definition and make sure to provide the proper target value, like this. The current timestamp stands for the exact time when a new row is inserted into the table. Additionally, we chose not to name this constraint. It's worth noting that some database systems see default constraints in the same way as not null, as an integral part of a column definition, so they don't support the naming of such a constraint, like MySQL, while some others do. If you're thinking about naming a default constraint, you can start with a simple question to generative AI tools and further look it up in the corresponding database system menu. So when would you find yourself in a situation that needs help from the default constraint? When you have a column that stores timestamp, a numeric column that you might perform aggregation on later, or an optional column that holds placeholder values. The most common scenario is definitely the first one. So let's dive deeper into that by answering two questions. First, does the default constraint replace not null constraint? Remember, we looked at this table. For the purchase time column in the purchase table, we added two constraints, not null and the default. They can't replace each other. The default constraint can't prevent users from adding null values to the corresponding column. So the answer to this question is a no. If you need to prevent null values, the not null constraint is definitely needed. The second question has something to do with the commonly used default values for timestamps, current timestamp. A common confusion on this is whether current timestamp adopts Coordinated Universal Time or the UTC automatically. Well, the answer to this question has two parts. First, it's safe to say that the current timestamp is widely supported by most database systems, such as MySQL, MariaDB, SQLite, and Postgres. However, when it comes to whether current timestamp adopts UTC or not is a totally different story. In some database systems, like MySQL, current timestamp adopts UTC automatically. So default current timestamp will support auto time zone conversion without any issues. But in some other systems, like Postgres, things are a little bit complicated. Whether current timestamp adopts UTC automatically or not depends on what data type you choose for the corresponding column. There are two different flavors for the data type timestamp. One comes with auto time zone conversion and adopts UTC automatically, which is a timestamp with time zone, while the other does not. If you are dealing with a database supporting users across different time zones, you want to use the one. If you are dealing with a database supporting users across different time zones, you want timestamp with time zone. Like this. You need to specify the data type as timestamp with time zone. By doing that, the default current timestamp will do the job as is intended. How to create a column representing the current timestamp and support time zone conversion is one of those things that you want to double-check by talking to a generative AI tool, and further look things up in the menu of the corresponding database system. That's everything about the default constraint. Let's move to the check constraint now. Check constraints are to some extent more capable and complex in comparison with not null and default constraints. Let's start with a simple question. What does a check constraint do? A check constraint is a rule that specifies a condition for a column so that each row must meet this condition to be considered valid for this column. For example, think about the table representing persons. The table comes with a few columns, like person ID, last name, first name, and age. The valid age number is between 0 and 120. The check constraint can check the validity of age values based on such a rule, and reject any data insertion or update that is considered invalid. When do you need to use check constraints? When you need to enforce business logic, set valid value ranges, or predefined datasets, or validate basic pattern, you can always rely on the help from the check constraints. Let's look at these scenarios one after another. First, enforcing business rules. As you conduct the requirement analysis for database design, you may gather some information about certain columns in an entity. Translating such information to SQL code requires the help from the check constraint. For example, think about a table representing book loans in a database supporting libraries. There are a few columns representing borrow date, due date, and return date of books. The rules that you gathered require that the due date to be later than the borrow date, and the return date to be the same or later than the borrow date. Enforcing such rules requires the help from the check constraint, like this. As you can see here, we start the definition of this constraint by naming it first. After that, we made two rules and concatenated them using the AND logic operator. Both rules are wrapped up in the bracket that follows the check keyword. The first rule says that due date needs to be later than the borrow date, and the second rule says that the return date needs to be the same or later than the borrow date. Such business rules won't get reflected in database design, but if they are enforced during database implementation, they need the help from the check constraint. The second scenario is range validation. When you have some columns that are numeric data, their data may not make much sense when they are not in a certain range. Although requirement analysis may not reveal such information explicitly, a qualified database designer can catch such issues and translate them into constraints. Remember the person table and age column that we visited a few slides ago. The requirement analysis of the database may not contain anything about valid data range of age, but it's not hard to deduce a valid range for human age and translate it to a check constraint, like this. For another example, think about a product table from a database supporting an online store. Its price column can use some help from a check constraint. If the price range is known to you, for example, between 1 cent and 1 cent short of a million, the check constraint may look like this. If the upper range is unknown, it could simply be like this. The next scenario is list validation. Sometimes you have a column whose valid values are limited to a small and predefined set, like transaction status or gender selection. In such a case, a check constraint can prevent invalid data from being added into the database. For example, think about a table representing user address in a database supporting an online store that only operates in US. So only 50 state names and DC should be considered valid. To make sure invalid data won't be added into a table accidentally like this, you can apply a check constraint to this column, like this. List validation requires the help from the in keyword. The syntax is relatively straightforward. State in that is followed by 51 state names, while the 51 state names are being wrapped up in a bracket. Of course, everything still needs to be wrapped up inside a bracket that follows the check keyword. The next scenario that often requires the help from check constraints is format validation. When it comes to pattern matching or format validation, SQL is not as strong as imperative programming languages, but you can still do many necessary and basic checking so that you can have this last line of defense to lessen the burden on the backend and front-end developers. One caveat about doing format validation using check constraints is the inconsistency across different database systems. Let's look at an example to demonstrate that. Think about the same user address table that we've visited. The data type of postal code is car5, which means a fixed size string. If we wanted to apply a check constraint to further limit it to exactly 5 characters long, the constraint may look like this. You may wonder whether this is redundant because car5 can already handle this task by itself. Indeed, it's unnecessary. But this is one of the few pattern matching syntax that is consistent across different database systems. Specifically, I'm talking about the like keyword. It is followed by 5 underscores that are wrapped up in a single quotation mark. That's how you express 5 characters. Can we go one step further by limiting the characters to be digits only? Yes, we can, but the syntax for that part will vary from one database system to another. For example, in MySQL, it will look like this by taking advantage of regular expression. In Postgres, you need to take a different approach, like what you see here on the screen. I'm not asking you to master format validation here. Instead, I'm asking you to have some awareness that you can do basic format validation in SQL as well, but the syntax varies from one database system to another. It's actually where generative AIs can help quite a lot, as long as your question is explicit about which database system you are dealing with. That's everything about using check constraints for format validation. In this video, we covered 3 constraints that can be handy during database implementation, including not null, default, and check, what they are, and when to use each of them. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment.